In this part of the video, I'm only introducing statements to prove and this complicated context. If you have watched my Euler video about the proof of Euler method, and you might have seen this context, you got used to it, but if you see it for the first time, it might look too complicated, but you have to be patient and just follow through what this context is about. So we start from x equals a. This is where our initial points are set up, and our initial value, y value, is y0, and here's our differential equation, y equals f of xy, and here's our initial condition. It's a standard condition. F has a continuous partial, and using more topological argument, you can improve that condition a little bit more, something called Lipschitz condition, but this is a standard condition in the continuous differentiable world. So that's our initial condition, and we don't know what this b and r is here, so then let me explain first what those are. R and b here is arbitrary, but we're going to make an adjustment after we set this r and b. B is to the right, and r is a positive number, so it's a center point here, y0 go up and below by the same amount. Once you put this arbitrary size of the box in here, maybe the solution of this one is inside the box, maybe not. It quickly escapes this box like this. We don't know. But by putting some condition, we can adjust its box. So we start from this arbitrary size. It could be one unit, a and a plus 1, or y0 plus 1, y0 minus 1, or y0 plus 2, y0 minus 2, whatever positive number you put it, so that we create this box. The next part is just adjusting so that we can guarantee something. Start from here. So this box is labeled D. The first thing we calculate is the maximum value of the absolute value of this two variable function on the right hand side on this plate D. Because of the extreme value theorem, this exists. Next thing we do is, with this m1 calculated, adjusting this b to a lot smaller value here. So maybe that was x equals 1, x equals a plus 1 here, but now we're going to make it possibly a lot smaller so that this function doesn't escape that box. If it escapes this box quickly, then we have to make this one really close to a, so that we cut it out here and capture it before it escapes this box. Hope that makes sense. How do we do this mathematically? Is the following. This r is this arbitrary choice of a number, and m1 is this maximum value. And if we divide this r by m1 and choose a number beta that is anything that is smaller than this quantity. So what this one is doing, this one will be the length of this interval right now. This is b minus a, but it had to be shortened to the beta somewhere here, such that the solution is not, if the solution grows fast, we have to capture within the box, so that it has to be a lot closer here. Think about it. If m1 is really big, that means the rate of change of this value is really big. So it's either going grow really fast or really small. It could happen. Not necessarily here, it could be over here, but it doesn't guarantee where it's happening. So just to be safe, suppose it's happening right here. m1 is close to the value of f of xy, it's close to m1 around here, then it's going to grow really quickly, so that we have to kind of adjust it. Turns out, if you look at the calculation, and you will see that has to be this amount. R is your arbitrary choice, divided by maximum. If m1 is large, you can see beta has to be small, so that you have to come really close in here. So that's what this adjustment is about. Just in case this has a really fast growth, we have to readjust the right hand side down to here and consider a lot smaller rectangle than what is shown here. Again, the purpose of this adjustment is to have everything within the box, so then we have some sort of control. We know how big the y values we're dealing with, especially if it is outside and we don't know how big those are, and there's no way to control it. So to be able to control those y values, we have to adjust it like that, so that y value is guaranteed to remain in this box. So that was the adjustment. So I think why this one works like this, I think it's a more efficient to explaining later is more efficient than now, but I think I at least explain the kind of little bit of motivation of the reasoning behind this one. So we have the smaller box, starting from A, going only the beta amount, if M1 is big, and this is going to be smaller. Actually, I'm assuming this beta is small enough so that it's even smaller than B and smaller than that one. So we're going to choose that beta smaller than B and smaller than this number, so that we're in this box and possibly smaller. If this B is already smaller than R over M1, then we don't have to adjust. We're going to just take that A and B. But it's possibly smaller here in this new box, and I label it by D bar. Let me say something about the absolute value of f of xy. It was before M1 was the maximum value over this big plate, but now it's a smaller plate, so M1 is not going to be the maximum value, but certainly it is less than M1, because still this one is still subregion of the original box D. So we still have this upper bound. With all that said, now I can introduce the statements of the existence and uniqueness theorem. First, we start with this iteration method. The first function y0 is a constant function, and all the other y1, y2 are inductively, recursively defined like this. The first statement is this. With that adjustment of beta, that's where this beta kicks in right away. These functions we're calculating is not escaping the box. Think about it. These are only the y values. I'm showing you the box here again. These are the y values, yn. This is centered at the y0. Above and below, it does not escape this the box. It's less than or equal to r. So yn, and difference with yn is somewhere here. The difference with y0 is less than or equal to r. So it's still inside the box. Of course, x is in between a and a plus beta, and yn, the values are less than or above this upper bound and a lower bound there. So with this adjustment, we can prove that all these points or functions we're calculating is within this box. Using that fact that all of them is within this box, we can prove that for any given x value in between a and a plus beta, and fix that x value there, and if you calculate that function value in this iterative way forever and ever, and it's going to converge to something. So this is important convergence part. Third part is the existence. Now you know this one given x value, these sequences converges, and we're going to define that as a function value. Given x value, the limit value is going to be the function value here. So if you define a function like that, the function satisfies this equation. This is the part that student might just skip. There's some fundamental part we have to touch here. When you go through this integral, and we need to discuss the continuity of this whole function, so that involves the continuity of this function yx, which was defined just pointwise above and did not discuss the continuity in here. So this is one of the theorem, just like the extreme value theorem and intermediate value theorem, that touch the very foundational part. It's never easy. It requires a lot of rigorous mathematics to establish the function defined here in this way is actually a continuous function. So we are skipping that part. That's too much of advanced calculus. So if you accept that the function defined in this way, this continuous function, then that function will have this integral value, therefore, and on top of that, we can show that function yx satisfies this integral equation. And it is easy to show ya is y0, the initial condition. If you plug in x equals a there, you can see it's just simply y0. So that's going to be the existence proof. Uniqueness will be stated as follows. Zx is a solution. In the existence, we showed that we exhibited that Yx, that as we defined before, is a solution. And suppose there is a solution possibly different from our solution. Then we show that any given x value in between a and a plus beta, the difference between this y and x and zx will approach 0. You know that this one approaches to yx, therefore this will prove that yx and zx is exactly the same value, because this converges to yx. So if you start with any other function, that must be the same value. So that's uniqueness. So we're going to take this one statement at a time and prove one at a time.